Decoding the future of AI. Welcome to AI Perspective. Imagine a world where the most powerful AI isn't locked behind a paywall, isn't limited by restrictive APIs, and doesn't tie you down to a single vendor. A world where cutting-edge artificial intelligence is free, open for anyone to use, innovate with, and integrate into their projects. Well, that world just became a reality. Miniaax, an emerging force in the AI landscape, has just unleashed M1, a million-token language model that has absolutely stunned the industry. This isn't just a big model. It's a game-changer. We're talking full book series memory, colossal 80,000 token responses, and performance that directly challenges models costing well over $100 million, all built for just $500,000. Let's break down the biggest number on everyone's mind: M1's context window. It's a staggering 1 million input tokens, with ample room for an 80,000 token reply. Now, if you're wondering what a token is, it's simply a tiny chunk of text, often a word or part of one, that the model understands. To give you some perspective, if you mashed all the Harry Potter books into a single prompt, you'd still be safely below 1 million tokens. This means M1 can effectively keep an entire book series in its short-term memory while it's writing. Compare that to the titans. OpenAI's GPT-4 can juggle about 1/8 of that. Claude 4 Opus can hold 1/5. Google's Gemini 2.5 Pro matches the million on input but has a shorter reply limit. And the well-known open-source contender, DeepSeek R1, tops out at 128,000 tokens both ways. In simple terms, M1 has the breathing room that other public models just don't. But holding that much text usually runs headfirst into the transformer's problem of attention cost, which balloons as sequences get longer. Miniaax, however, sidestepped this entirely by cleverly combining two revolutionary ideas. First, the model uses a mixture of experts' design. Think of it as 32 specialist submodels that all share one central brain. Each token only wakes up a handful of these specialists. So, while the entire model boasts an immense 456 billion parameters, only 46 billion are active at any given moment. This makes it incredibly efficient. Second, they swapped the classic every token looks at every other token attention mechanism for what they call lightning attention. This is a linear technique that keeps the mathematical cost almost flat as the prompt grows. 7 regular transformer layers sit on top of each lightning block, so the model still keeps the strengths of the standard architecture. But most of the heavy lifting happens in this lighter, more efficient mode. The payoff is crystal clear in their graphs. When M1 generates a 100,000 token answer, it burns through only 1/4 of the floating point operations that DeepSeek R1 would need at the same length. And at 64K, it's under half that. This incredible efficiency also translates directly to the price tag for training. Miniaax completed the entire reinforcement learning stage in just 3 weeks on 512 NVIDIA H800 graphics cards. The total rental cost? A mere $534,700. In stark contrast, DeepSeek R1's team reported spending between $5 and $6 million, and early estimates for OpenAI's GPT-4 training broke the $100 million mark. This massive difference in cost comes partly from lightning attention's low floating point operations, but also partly from a fresh reinforcement learning algorithm that Miniaax calls CISPO, short for Clipped Importance Sampling Policy Optimization. Traditional policy optimization, or PPO, which many labs use, avoids instability by clipping big gradient steps for tokens that were unlikely in the previous model pass. Unfortunately, those rare tokens often hold the wait let me rethink moments that real reasoning depends on. So PPO can effectively strangle creativity. CISPO flips this rule. Instead of cutting off the gradient, it caps the importance sampling weight and lets every token keep contributing. In Miniaax's own tests, CISPO hit the same math contest score in half the number of training steps as its closest competitor. Before any of that clever reinforcement learning work began, Miniaax carried out another 7.5 trillion tokens of standard pre-training. They used a data mix that was 70% STEM, code, books, and explicit reasoning. They then ran a supervised pass that injected long chain-of-thought answers so the model would naturally lay out each step of a solution. Only after this foundation was solid did the reinforcement learning phase kick in, and the curriculum there is truly fascinating because it mirrors how humans learn. First came tasks with answers that could be checked by handwritten rules. The team cleaned tens of thousands of real competition-level problems from the American Invitational Mathematics exam. They also generated 53,000 logical puzzles, everything from cipher grids to Sudoku variants, using an internal synthesis tool, giving each puzzle a strict verifier. They also collected 30,000 competitive programming tasks, and where the original websites lacked tests, the older Miniaax Tecton 01 model produced comprehensive test suites so every code solution could be compiled and run. For a taste of real software engineering, they even mirrored GitHub issues into a sandbox that could build and test actual repositories. This means the model had to read a bug report, locate the broken file, write a patch, and prove it works by passing unit tests before earning a reward. Absolutely brilliant. The second batch involved tasks with single correct answers that are hard to catch with pure rules, such as detailed science questions or tricky factoids. Miniaax trained a generative reward model called GenRM by comparing human-labeled answer pairs and tuning it until the system reliably picked the better response. Finally came open-ended conversation, writing, and instruction following. Here, GenRM used a simple three-way judgment: better, same, or worse against a reference answer that itself was selected through a Swiss round tournament among outputs from several strong models. Throughout, the engineers meticulously monitored GenRM for length bias, ensuring the model wasn't just handing out extra points for longer replies without real gains in accuracy. Miniaax also had to keep the training run from crashing. They spotted that probabilities inside the training loop didn't match what was seen during inference. The culprit was low numerical precision in the final language model head, so they switched that layer to full 32-bit floats, and the mismatch vanished. Another headache was output loops, where the model would occasionally fall into a repetitive pattern, churning out boilerplate for thousands of tokens. To prevent the model from getting stuck in a loop where it keeps repeating itself with full confidence, they added a simple rule. If it writes 3,000 words in a row with super high certainty, it just stops. With everything stable, the team pushed the model's reply length step by step, gradually expanding the limit. Each jump forced them to rebalance the dataset, because in later stages, bad answers tended to run longer than good ones. They addressed that by mixing sample level and token level losses, tightening gradient clipping, and lowering CISPO's clipping bound. So how does all that translate into real scores? On the AM 2024 benchmark, the 80K version answers 86% correctly, just a notch behind the freshly patched DeepSeek R1 and comfortably ahead of earlier open-weight models. On Live Code Bench, it lands at 65%, matching the Big Quen model and trailing DeepSeek by only a few points. In software engineering, M1 truly leverages its fine-tuned sandbox skills, repairing 56% of issues on SW Bench, a fraction shy of the latest DeepSeek but well ahead of everything else you can download today. But perhaps its strongest suit is long context understanding. On the 128,000 token version of OpenAI's MRCR benchmark, M1 posts 73.4, beating both Claude 4 Opus and OpenAI's O3, and sitting second only to Gemini 2.5 Pro. On the million token MRCR, it still clears 56, and Longbench V2, which goes up to 2 million words of context, shows just over 61. For tool use, M1 scores hover around 62 and 63, outpacing every other open model, and even edging ahead of Gemini in some runs. One fascinating pattern shows up in the training charts Miniaax released. As reinforcement learning steps tick upward, the average answer length on math and coding problems climbs past 20,000 tokens, and the accuracy curves rise almost in lockstep. In other words, letting the model think out loud for longer genuinely improves the final answer, provided the underlying attention can keep costs down. This is the philosophical bet Miniaax is making. Extend test time, compute efficiently, and you get smarter models without simply scaling parameter count. If you're eager to try M1 yourself, the company suggests VLLM as the serving backend because it handles large expert models with smart memory pooling. But you can start with the standard transformers library if that's easier. The repository includes structured function calling, and the demo chatbot plugs in online search, image and video generation, text-to-speech, and voice cloning. This means you can build a fairly complete assistant or agent without adding external tooling. And because the license is so permissive, you can even keep everything on premises, which is incredibly appealing for companies with strict data policies. This is the full story for now. All the code, weights, and the technical report are linked in the description below if you want a deeper look. Thank you for staying with me on this incredible journey into the future of AI. We'll catch you in the next video.